Hi, everyone. My name is Justin Lay. I'm playing on behalf of Anduril. We've been doing embedded Haskell for a long time in real-time systems. And the first thing people ask me when they hear what I'm doing Haskell embedded system is, first of all, like, what does that even mean? Like, how does Haskell run on a chip or anything? So we have accumulated a lot of tough lessons learned, a lot of general principles we've built over the years, and it's kind of a quick, rapid-fire knowledge dump and experience report. So it's not a structure, it's kind of just, I've made 3 general categories of lessons and areas that are worth looking at. And if you have questions at the end, I'll kind of clarify, but this is more like a knowledge dump and experience report than like a unified, nice, tidy little bow of things. And so why Haskell? Haskell started before I came there, almost at the start of the company, actually. So we had kind of a lot of requirements within the project. We needed to coordinate sensors, peripherals, and other outputs, FPGAs, CUDA cores, all that, and low-level flow systems, which are usually interfaced using C in most languages. We need the layer of orchestration between those things to be very reliable, and we need to be able to encode business logic very well in a way that there's no logic errors or crashes. We need to deploy this across multiple heterogeneous machines with different capabilities, with different hardware, even different architectures between like x86, Arch Linux. And we need to have multiple devices, multiple products that each deploy very differently. So I think overall the question, why Haskell? I think if you're here, you probably know the answer is why not Haskell, right? If you're here, you definitely have the drive to put Haskell everywhere. I think it works very well because the low-level embedded programs, CUDA code, the FPGAs, the serial bus interfaces, everything else runs below the socket level, below the kernel level, but the Haskell is what orchestrates them all together. And we need that layer to be very, very secure, very type-safe, and very reliable. And it's kind of a little graphic of one device has multiple machines on them. These are different Linux boxes. They're running NixOS. So the machines, they have sensors, they have GPUs, all interfaces using sockets or serial buses, some even using USB. All very low-level interfaces. They bubble up through the Linux kernel, and Haskell lives right on top of that in whatever memory we have left on the machine. So the Haskell space does have, the full Linux. We have RAM, so we're not constrained in terms of the Haskell aspect, but we don't have a lot of RAM. We have just a limited amount. We can't just write memory leaks forever. Our things have long-living processes. So we have one device, multiple machines. These devices here have low-level things. Some of them are just purely Haskell devices that only run Haskell processes, Haskell daemons, Haskell servers. We even have some devices that serve the UI to users, and they run Haskell backends within the same device. We're working on using Haskell in the UI as well with JCJS. So hopefully this can become more and more Haskell. Maybe one day there'll be even more Haskell in the kernel as well. So this is what we mean when we meant Haskell, embedded Haskell. We're not writing FPGAs in Haskell yet, but we are servicing the orchestration layer and the process between everything in Haskell. So some lessons on the low-level aspects. Haskell is actually the best C build system we've used, or Cabal is. Cabal is really great with integrating extra libraries, extra source files. So if you ever need a C build system, even if you're not using Haskell, I would just use Cabal anyways. Everything works so well. There's been a lot of great work. It even builds C++ very well too. So C++, everything integrates very well with Cabal. So if you're working with C code, Cabal is great. There's so much work on that. Everything we've built is orchestrated using Nix and NixOS. I know there's a big overlap between NixOS people and Haskell people. This is where it all works out very well. So all the firmware, all the integration with the foreign headers that Haskell pulls in through FFI, NixOS handles very well. We do a lot of code gen using NixOS that's integrated into the Haskell system. So NixOS can read documentation, can read module specifications, it can read C bindings. generate those bindings as Haskell libraries, and now those live inside your local package. So you can just add in a C header library, hopefully even more smoothly with well-typed HS bindgen. So you import your C library as if it was a Haskell library, and it lives in your Haskell space right away with NixOS. And there's a lot of fiddling with CUDA and accelerate that is really tough using multiple systems, heterogeneous systems, and NixOS handles that very well, so we don't have to worry about any CUDA dependency mismatches. It all just works out of the box. We try never to use the D word. We don't use Docker. Everything is within NixOS, so using the most recent Linux features, systemd, C groups, Haskell running as systemd processes, and with Nix, everything just works well together. I can't imagine a better glue layer than Haskell for business logic. And yeah, we definitely leverage Linux. We have shared memory buffers in the RTS, so Haskell has the ability to copy off shared memory, so multiple Haskell processes can share memory with each other. So you can pull, so let's say you have a sensor that detects maybe data from a room, like heat temperature. You can get that off the FPGA right away in PCI bus, pass it to detectors across your whole process, your whole computer, your whole OS, and never do any single copy. So zero copy sharing between FPGA, PCIe, and all your actual data processing systems because of how well Haskell integrates with the Linux runtime and API. Some unfortunate lessons we had to learn early is definitely instrument early. There's a lot of nice Haskell libraries for instrumentation if you're not aware of them. EKG and StatC are great out-of-the-box solutions for very easy instrumentation and monitoring. Those hook up straight to the Grafana and other UI systems that you can just have a nice dashboard right away. There's no kind of upfront work to be done, very little. So it's just as integrated as most other ecosystems. And also with Brick, building TUIs is super simple, right? If you've ever used a Brick TUI, the startup time from pulling in data streams to having a fully functional TUI is very small. Sorry, a terminal UI. So it's a graphical on the terminal with libraries like a GHCUP, like graphical interfaces on the terminal. So I guess I wish I had an example, but just terminal interfaces, yeah, graphical terminal interfaces. And also it's good to respect the hierarchy. Cycles at our level are cheap, threads are cheap, but FFI and I are expensive. So utilize thread scope, and GDB works very well as well. GDB works very well with Haskell processes in case you haven't tried it. Thread scope helps you very easily spot FFI syncs. There's a big potential for FFI between C processes to lock the whole system, the whole runtime together. And it's really easy to spot those in GDB and thread scope and just eliminate them right away. There's not much headache and it's easy to just dig into them. It's not as bad as you might expect. It's good to, another lesson is have progressive capabilities, right? Haskell, you can serve many different types of servers. We end up serving gRPC and HTTP2 for our interop with other devices. We have Servant, HTTP1, very simple to have simple web sockets and other servers like that. At the low level, we have things like raw TCP using CBOR for incremental serialization. If you ever use the libraries like serialize, they let you give message framing. So you can have very efficient binary serialization in Haskell very well between processes. And another low-level thing are hooks on actual file descriptors. So if the top level fails, if the UI fails, if the HTTP2 fails, we have HTTP1. If HTTP1 fails, we have TCP. If TCP fails, we have file descriptor hooks. So at each level, there's progressive safety and assurity. So your very important processes that need to keep running, we have things like CBOR and serialize on TCP. The very high-level things that can break down, maybe UI might break down. UI can be allowed to fail. We have higher interfaces for that. And the Haskell runtime is very good at balancing out those different layers of failure. And as long as you keep tight handshakes across procedures, Haskell's greatest strength is type safety is across the board useful. We have type safe TCP, type safe file descriptors, Just never forget why we're using Haskell for that nice type safety. Along that line, I think I want to say what we agree as a whole company is Haskell's #1 killer feature. Anyone want to take a guess? I gave some examples, but the real answer is not here. Yes?
STM?
You did guess. It was STM. It is STM. By far, it's the most bang for the buck in terms of working with these type of things. Why? Because we have an STM universe, and everything works together very well into a nice denotative system. No need to have extra libraries. It just all fits together pretty well. Between pure STM, we have concurrency. We have hardware STM, which we use STM to wait on file descriptors across memory, across hardware. You have time-based STM. The whole universe works all very well together. It's just kind of a beautiful way of describing the whole system. Everything hooks in. The more we hook into it, the more we can use from it. So it's like an n-squared type of networking effect of benefits. Let's see, like a little bit of control flow. Workers, we want to avoid immortal threads, maintain system coherence instead. All this is done using STM. We really don't use monad transformers that much. We like just having context to IOA. It's kind of enough for a lot of things. Streaming combinators, when I first started, I streamed everything combinator that used every library I could think of, and over the years, I've rolled them back. They're very useful and powerful for prototyping, but if you know what you want, just writing the quick loops ends up being much more effective. So I love streaming combinator libraries. I built a lot of my career on them, but the more flexibility you get, when you know what you actually want, you start rolling them back, and they roll back pretty closely well to like actual real-time loops. Lifetime management, using with X bracket continuations works well, and remember to use resource T and acquire for scoped regions of memory. Do not be tempted to use these to manage heap memory. These only manage kind of external life cycles. We have issues with like people using resource T for heap memory management, but it's more for life cycles and resources. And kind of a final wrap up, every Haskell there's two goals, I'd like to say. This is definitely my daily journey. We want to build beautiful type-safe abstractions between semantics, or we want to just have like psychographic safety, make it simple as possible and usable. And there's a constant battle, even in the industry. Here's some quick summaries on Haskell language features that we've tried out and rolled back. Compiler optimizations, we definitely assumed a lot of optimizations that didn't happen. So we had to go back and manually vectorize, manually optimize, manually inline. It's not magic, but it's pretty close to magic, but it's not 100% magic. We get a lot of bang for buck out of dependent types using length index types and state index types. A lot of times, building these bindings for C APIs, having those types clarifies the APIs very well for anyone to use. But always provide a nice untyped interface for people who just want to do things unsafely. Our configuration is type safe. We use a type safe configuration language that isn't Haskell, and it supports JITs. So if your config language is safe, you can actually integrate everything. The whole system of configuring your systems and everything is also type safe, and you don't have the mismatch. So you get a lot of benefit out of that. And when we have CUDA and accelerate using CUDA compilation, we definitely have more type safety there. So there's a lot more that can be built into the type safe world than you might think initially. Some closing thoughts. I think it's nice to say a simple Haskell scales for just using simple procedures, simple I/O actions, and context passing along. It definitely goes a long way. STM is in base, and it definitely goes a long way as well. The synergy you get out of Haskell, Nix, and Linux is very hard to understate, how things just fit together so well. And a lot of great work has been done into making that airtight, and I really appreciate it. STM definitely, I think, is JIT's greatest asset for this type of project. We want to emphasize using progressive capabilities for reliability. Things can fail, but make sure that there's always a level that doesn't fail. That can be in Haskell. Manage the resources principally, and never abandon type safety totally. Yeah, that's my rapid fire. These any questions, but hopefully I've convinced you if you're doing embedded work or work with very fast systems, memory systems like CUDA, FPGA, then this gives you the confidence to start that at your own company.
Thank you. We have time for questions, and in the meantime, Phil, can you set up because you just... So, questions from the audience? Okay, the one from platform.
Yeah. This is
When I think of embedded Haskell, the thing I worry about is like memory and garbage collection and things like that. Is that not a concern for you?
Yeah, the underlying systems are written in FPGA or other fast libraries in C sometimes, or CUDA. The Haskell layer is simply the orchestration. So as long as you keep your actual memory in the Linux space, not on a heap clean, then as long as the orchestration stays safe, then you have a lot of room for memory usage.
Hello, is this on? Okay, thank you for the good talk. You said that you use Nix, and in my experience, working on GHC, also using Nix and Flakes, I have to run Nix collect garbage-d quite frequently. So I'm wondering what your experience with the Nix packages and Haskell Nix ecosystem is, if you can comment on this.
Yeah, the development process, if you can, a single closure, we have a lot of room. We usually have to we can go months without like a garbage collect side of the closure. The main things are upgrading the CUDA dependencies. That's like a huge chunk of space for some reason. But as long as you don't update that very often, then it's very easy to maintain sharing. There's a lot of like sharing between NixOS, right? Most libraries are shared. There's no extra space needed for that.
Can you say more what you mean by the STM universe?
The STM universe
is kind of like it's a library with some powerful combinators for concurrency, but I get the impression that you've built some kind of library infrastructure underneath that you might want to share.
Yeah, actually, we haven't built that much, but we're using things that other people have built, right? There's the async library, which uses STM to manage threads and workers. The STM manages file descriptors pretty well. You can wait on file descriptors, wait on hardware inputs. So within one atomically block, you can call across I/O, hardware, threads, all managed in one nice atomically, right? So if I want to wait on this descriptor, this hardware, this thread, and this message externally, they can all be done in one single atomically, if that makes sense. So the more you get out of that, the more n-squared network effects you get out of the benefits there.
I don't think there's a paper associated with this talk. Is there somewhere with more details on the implementation details of how you've done these things? It feels like you've got some recipes that could be reused by people, and I want them. Yeah,
there isn't yet, but if there's interest, I will work on like doing some more publishing work. I do run my blog, and I'll try to update things as I can.
I would appreciate that. I love your blog a lot.
Yeah.
Okay, any other? Okay, well, exactly, I have a question. So I imagine that the more you can cover with Haskell in this distributed and very multi-component system, the easier your life would be. So which would be the number one area where you can't apply Haskell, where GHC doesn't work out, or maybe you even tried and it didn't work out? What would be the number one where you wish that Haskell could expand into in this heterogeneous system?
That's a good question. We are working on getting Haskell more smoothly in the UI aspect of it. Haskell in the FPGA would be nice. But there's actually very little code.
I know someone who could
Yeah, of course. And we're actually slowly converting things in Haskell all the time. Like we recently converted a bunch of kind of LabVIEW code into Haskell, and just overall, just it's a slow process, a slow march of eating up everything we can, because we're very hungry.
Okay, thank you. Thank you, speaker again.